Everyone, thank you. Yeah, I'm Lois, and I'm going to talk to you about two sort of separate things today, but they are inextricably linked. The first being my self-built journey, and the second being how that has then fed into my PhD research. It's not working. Oh, hang on. Oh, it's doing something. It's just loading that menu instead of scrolling. Okay, that's all right. We can manage. So, inspiration for my life, I suppose, slightly far-fetched. But when I was just about finishing school, Grand Design was on the telly, and I saw this ecological building, and it was impressive and inspiring. John Bodger, it turns out, is actually my dad's cousin. So I felt like I had a connection to this house. John Bodger was the architect. Additionally, there was the Woodland House by Ben Law. You've probably all seen these programs. They're inspiring buildings. But that really kick-started my urge and my kind of belief that it was possible to build my own house one day. So a few years later, this became the property that me and my husband owned. And it is a 1980s former battery house on the River Lune in Lancaster, just outside of Lancaster. It's a solid stone building, has a south-facing aspect, one of those classic hard-to-treat properties, detached. It's built into the hillside, so we've got some different elevation, different levels going on at the front and back elevations. Then internally, we've got high-vaulted ceilings. There were some good interior fittings, these nice hardwood stairs, beautiful tartan carpet everywhere. I cannot express to you how much I now loathe tartan carpet. But underneath the tartan carpet was this solid concrete floor. And then, oh, menus doing things again. Okay. Yeah, and then the layout inside was kind of divided into these four segments. We had 2 stories on the left-hand side, a mezzanine on the right, a porch at the entrance, so you couldn't actually walk into the building, you had to walk in and then go along and then go around, and it was all a bit convoluted. Mirrored staircases, which looked impressive, but took up absolutely loads and loads of space. And then it wasn't a house when we bought it, it was an office. So we had like this pokey little tiny kitchen that was just about big enough for a fridge and a microwave, and a ladies' toilet and a gents' toilet, and no bathroom and no shower. So it was an interesting starting point. Anyway, there weren't many windows, so it was quite gloomy inside. And of course, you think, oh, this is going to be an amazing project. And then a few months later, you're like, what the hell are we doing? Anyway, we had big ambitions. We wanted to retain its character. We wanted to see it have excellent thermal performance. We had to insulate all of the external surfaces. We wanted it airtight. We wanted MVHR. We wanted to improve the layout and the flow. We needed a bit more space in terms of storage and living space. So we wanted this small extension on the side, which we put on with a green roof. That became a workshop, utility, and bike storage area. To the rear, we wanted an extension which facilitated removal of one of those staircases. We wanted to obviously do all of this, protect the building's longevity, and we wanted to use sympathetic and low-impact materials, which brought us to what should we retrofit with? And of course, there's loads of options. Which is the right one? So when you're thinking about what products you're choosing, you've got various different factors affecting your choice. Suitability, performance, how easy is it to install, how much does it cost? And then for me, because I studied environmental science, I couldn't get beyond this environmental performance. What's its bigger impact on the environment? And it got me thinking about what's the embodied energy of these things that I want to install because I want to save operating energy. And when I questioned this, I was unable to reconcile and figure out any answers, because in 2015, this wasn't really a conversation that many people were having. So that was kind of the birth of my PhD, and I was fortunate enough to find some funding, went and quit my job and went back to university. And I spent the first few months of my PhD doing a literature review, as most PhD students do. And I came across this graph, which really, really captured my attention. The graph, I'm going to try and explain it thoroughly, because when I showed it to my husband, he didn't get it at all. Basically, when we're talking about a life cycle, we have got to add together embodied impacts and operating impacts. And so the sum of these things becomes total or life cycle energy or carbon. So this graph here is documenting a range of different building types and categories along the x-axis: conventional, low energy, passive house, self-sufficient, in inverted commas, because the only one there that has a definition is a passive house. Then up the y-axis, we've got energy requirements for those particular buildings. The yellow line is showing operating energy for those different housing types. And we've got 4 data points. Each one of those data points has its partner data point on the operating energy line. And this graph conveniently suggests that when we improve our operating energy, i.e. The operating energy gets less, that our embodied energy begins to increase. And that's shown by the total energy line, which has an inflection point over passive house. All well and good. But can we actually apply this to retrofits? So the next part of my literature review involved gathering lots of data. And I gathered data from loads and loads of different peer-reviewed scientific papers, which were looking at both new build and retrofit projects. These are all domestic. There's a lot going on in this graph, so bear with me again whilst I explain it. As in the figure before, we've got operating energy along the x-axis, and it decreases. So effectively, we might have the conventional houses at that end, and the passive houses are down at this end. We've got energy up the y-axis on the side. And then if we were to plot the operating energy of all of those buildings, then we're actually plotting operating energy on the y-axis against operating energy on the x-axis, which makes a y equals x straight line right the way down, which is shown there in gray. Now, when we come to the embodied energy, that's where all of these colorful dots begin appearing. We've got 6 different categories there. The top 3 in the yellow squares, green circles, and green diamonds represent new buildings. Then we've got different life cycle methods that were used to derive those data points, which is why there are 3 categories for new buildings and 3 categories for retrofit. So apologies, it's cluttered, but it was necessary. I couldn't plot all of those data points within one series because it would have been methodologically incorrect. But the important takeaway from this graph, once you get your head around it, is that all of these lines are kind of flat. They're not going up like the graph that we just saw, which is suggesting that embodied energy is actually not increasing as our operating energy improves. So I've just here pulled out the retrofit specific data. So it's exactly the same graph, just zoomed in on the retrofit data only. And in fact, on the retrofit, the pink one, we are seeing a slight increase in embodied energy. And arguably a very slight increase on the blue line as well, but certainly not a very, very massive increase in embodied energy with decreasing operating energies. But I think this goes to show that from the graph, the like conceptual graph before and the data that I've collected, it demonstrates that there's actually a bit of a gap in understanding about the relationship between embodied and operating energies, specifically and particularly in relation to retrofits, which got me to asking my research questions. So can we identify that balance point wherein we can have quantifiable parameters for whether or not we proceed or don't proceed with a retrofit in life cycle terms? There are some issues around life cycle methods, which I have spoken about previously, which I'm not going to go into today. But can those methods be better than they currently are? Specifically, again, to help us identify the optimum retrofit. And again, I'm not going to talk a lot about this today, but there are issues around data and data certainty and data availability that make quantifying the life cycle impacts of a retrofit really, really difficult. So is there adequate data available to provide certainty in those analyses that we're undertaking? So broadly, the approach that I then took for my subsequent research was to look in detail at what life cycle analysis is and understand where its limitations lie in terms of delivering design advice or a design decision point for construction. I then took that and developed a specific set of criteria that we can apply to a retrofit lifecycle method. I then developed this idea of this retrofit tipping point, which I will explain in a moment. And I brought all of that together by testing it with a couple of archetypal case studies, which I will explain also in some more detail shortly. So my retrofit tipping point, I've already said life cycle impacts are equal to the sum of the embodied and operating impacts. Now in a retrofit, we've got to appreciate that it's a bit different to a new build. When we're building a new build, we've got a new burden of operating impacts. We also have a new burden of embodied impacts. And so the entirety becomes this new burden. In a retrofit, we've got this kind of paradoxical situation where we want to save operating impacts, but the way to save operating impacts is to spend embodied impacts. So we need to marry those two up really, really carefully and find that balance point wherein we're not exceeding our savings in operating by spending too much in embodied. So the retrofit tipping point that I propose actually looks at the change in operating energy or carbon and looks at the ratio between those two, specifically focusing on savings rather than just the resulting operating impact. So, as I said, I've developed this method for retrofit lifecycle analysis. First of all, we use PHPP to collect the pre and post retrofit operating energy. Because PHPP works to standard conditions, and that's not actually very realistic when we are looking at the specific buildings, I have also modeled my work using the Ofgem energy use average of typical UK dwellings. In reality, I would propose that we also take meter readings or use occupant conversations to derive a good estimate of their current operating energy use. I then took the RICS, the Royal Institute of Chartered Surveyors, Whole Life Carbon Guidance, 2nd edition, as the basis for my life cycle methodology. I've made a few changes. So the column on the right-hand side is the changes that I've made. Basically, at the very top there, we've got life cycle stages. The RICS methodology doesn't include energy beyond the stage. Well, it doesn't include energy, full stop. It is just a carbon analysis. And I've explained previously, again, I'm not going to go into it today, why it's really important that we look at embodied and life cycle energy as well as life cycle carbon. So I was unable to do a full life cycle energy analysis, but ideally I would if we could get the data. Looking at lifespans, chatting with Hannah about this yesterday, using a 60-year lifespan to evaluate a building is a bit weird. I mean, I can see why it's necessary because we need to standardize our methods so that the results are comparable between one analysis and another. But we actually should be looking at a more realistic, specific evaluated lifespan per building and run the analysis and make our design decisions based on that result. Then, because I'm interested in the retrofit that is reducing operating energy, I want to understand the works relating to the thermal upgrades only. You know, if we're changing other things at the same time, that's all well and good. But for my analysis, we have to look just at the thermal upgrades. So that then means that we will report on the impact categories relating to energy use for pre and post retrofit, heating, cooling, and ventilation. So just the space conditioning. Reference that to the treated floor area because including gross internal area doesn't well represent the effect of the retrofit impacts. A couple of other things there. I exclude existing assets because the life cycle method proposed by RICS includes maintenance of the building, but in a retrofit, the building already existed. So the maintenance impacts are not attributable to the retrofit. The maintenance impacts are attributable to the building. So we need to exclude the existing assets and maintenance and so on that's associated with that. And then finally, I also exclude any on-site energy generation or equipment because you know, those are not related to the building fabric. Am I nearly out of time already? Okay. So I haven't got to the interesting bit yet, sorry. I'm going to skip through a bit of these. A reminder of the, so there's some content here that's just for your information if you're reading your slides later. These are the life cycle stages and their names. Then these are my case studies and variants. So Broadway was a Victorian mid-terraced house. It represents 28.4% of all UK housing because it is a terraced house. Northern aspect, solid stone walls. You can look at the details at a later point. And Waterview Lane was the other case study. It was a 1950s semi-detached cavity wall. The semi-detached archetype represents 25.3% of UK housing. Had a suspended ground floor, ventilated slate roof, and it had a few minor upgrades prior to my retrofit. These are the key parameters for those case studies. We've got really similar treated floor area, window area, and occupancies, but quite dissimilar external wall areas, adjoining walls, and form factors. And that's because it's a semi-detached and a terraced house being evaluated. I should say as well, the retrofits that I designed are hypothetical. But they were designed to be ambitious. They didn't have a specific target in mind, but they were representative of what I considered to be a realistic, good retrofit, deep retrofit. And then I took the original options and multiplied them by modifying a few of the elements so that we've got more data with these different variants. So just reminding you about our tipping point. You've all remembered what that is. And now I can move on to my results. So Broadway was the terraced house. We can see that the embodied energy savings are, hang on. Yeah, the embodied energy that we spent, sorry, was nearly 10 times smaller than the operating energy that we saved based on the Ofgem data, which is shown. The Ofgem data is shown in the darker blue. The PHPP data is shown in the paler blue. The PHPP savings were greater because the PHPP starting temperature, you know, building condition was at higher temperature. So essentially it used more energy before we did the retrofit. In carbon terms, we see a very similar story. Because the carbon data was available, we've got carbon for the full set of life cycle modules. And you can see that broken down. And then I've looked at the embodied impacts according to these functional categories. So we can see that in both energy and carbon terms, we are spending most of our embodied impact at the insulation, on the insulation, with doors, windows, and consequential works also playing quite significant contributions. Consequential works is stuff like building a bulkhead around a ventilation duct, for example. The dominant life cycle phases are the product stage, which is the large yellow bars, and the transport stage, which is the green bar, and 5.2, which I have forgotten, and I've written it in my notes here. Yeah, construction activities. So we can start to pull out where the major impacts are happening. So that was Broadway. Waterloo Lane, I'm not going to go into detail because actually you can look at this at a later point, but importantly, it's a really similar pattern. The only major difference being that the savings at Waterloo Lane, which is the semi-detached house, are smaller than the savings that we made on the terraced house. So the overall impacts actually were smaller. So going back to the graph from the beginning, where I plotted literature data, the data points in the lower corner here represent my case studies, and we can see that they are in the same order of magnitude in terms of embodied costs, and they represent a slightly better performance than most of the data that was already available. Looking at the carbon data, which I hadn't plotted previously, we can see that I've plotted carbon here, embodied carbon against operating energy. Again, it's in this reverse order, but the embodied carbon, again, is really, really flat. So it doesn't matter what the resulting operating energy ended up being, the carbon expended was still more or less the same according to this small data set. So in terms of the original conceptual diagram, we can draw a straight line instead of a curve for operating energy. We can draw a flat line for embodied energy, and we can basically, I think, dismiss that model. We need to then work out what model is useful when we're looking at retrofit. So this is the embodied energy plotted against operating energy savings, which is the distinction between the graphs I presented earlier. And we can see that none of the, I'll just mention that the open circles represent extrapolated data, so it's not actually, that was because the energy wasn't available for its whole life cycle. So I extrapolated the product stage energy data up with the same relationship as the carbon. So energy on the left, carbon on the right, but none of the embodied impacts exceeded the operating energy savings. So it suggests here that all of the retrofits were advantageous over their life cycle. And then finally, this is the bit that excites me. I'm sorry, I've got to the end and I'm probably running out of time, but this is the really exciting bit. When we look at the carbon intensity of renewable energy development, we're seeing embodied carbon in the ranges between 5 and 100 grams of carbon dioxide equivalent per kilowatt hour of renewable energy generated. Then my case studies, I was able to put into a comparable metric. So the carbon intensity of retrofit is comfortably within the range of the carbon intensity of developing renewable energy. Now, this is important because it means that where we are developing policies for decarbonisation, if we are focusing only on renewable energy, we're missing all of the savings that could be made by decarbonising our homes through retrofit at the same time. Now, importantly as well, if we proceed with decarbonising our energy systems, but then decide that for comfort reasons, we want to do the retrofits at a later stage anyway, then we'll spend that carbon for the retrofits, having already spent the carbon on the renewable energy. So for policymakers, this kind of data is really, really valuable. I've only got 2 data points though, so I need to do some more research on this. And if anybody's got any funding that they would like to deliver for me to carry on with my research, then I'd be really appreciative, because I can't carry on doing it for free. But yeah, that's the kind of headline results from my PhD. You can read the key points later, but yeah, thank you very much. Sorry, I went a bit too long.